come on, not again.
Sorry.
It can only handle one tool at a time.
I know, I'm sorry, I forgot. I'll flip it back on.
What's taking so long is just a switch.
All right, we should both be able to use our saws now.
What'd you do?
Don't worry about it.
Select each object to learn what electricity is and how it works. An electrical circuit is a path or group of interconnected paths through which electrical current flows. Electricity is the movement of electrons that travel in an unbroken electrical path, leading from the power source to the point of work and then back to the power source again, creating a circuit. The point of work is wherever electricity powers light bulbs, machinery or equipment, and other places where the electricity provides power. In a simple circuit, the battery is the power source. Circuits begin and end at the power source. In the workplace, the power source is the electrical installation, which sends out power to all the workplace's electrical needs. Typical power sources are breaker boxes or power outlets. Current is the flow of electrons through a conductor. The volume of electricity delivered is measured in amperes or amps. A typical household electrical circuit draws 15 amps of electricity, while industrial workplace circuits can draw several hundred amps. However, there is more than enough electricity in even a simple household circuit to supply the fraction of an amp of current required to stop the heart. Electrical current needs a conductor, something physical to travel through. Examples of conductors include copper wire and metals like aluminum and steel. The human body is a good conductor too, especially when your skin is wet or sweaty. Electricity doesn't travel well through insulators. Insulators isolate electrical components and prevent current flow. Examples of good insulators are rubber, plastic, porcelain, and glass. The rubber or plastic casing around wires, the rubber soles of your boots, plastic tool handles, and glass insulators on power lines are all insulators that resist the flow of electricity. Unfortunately, no insulating material will keep you 100% safe. Electricity naturally travels to the earth, literally the ground. When setting up electrical circuits, a ground is a safety feature that diverts an electrical system's current safely to the ground and rapidly trips the circuit breaker, shuts off the electrical flow, to remove the electrical charge from the circuit, protecting the circuit and the workers near it. A ground is often the steel frame of an appliance, copper pipes in a house, a metal rod buried in the dirt at a breaker box, or a round prong in a standard receptacle, all of which provide a pathway with very little resistance directly to the ground. An electrical hazard is a dangerous condition that occurs when your body contacts live electrical parts, when equipment fails, or when electricity reacts to an unsafe environment. Bodily contact, equipment failure, or an unsafe environment can result in an electric shock, arc flash burn, thermal burn, or blast. Select each object to learn how electrical hazards and injuries commonly occur in the workplace. After reviewing the content, select the X to return to and learn about the remaining images. Unsafe work practices can cause or contribute to electrical hazards. Hazards occur when workers contact live wires, such as overhead and buried power lines, and other energized sources or exposed electrical parts. Workers may also become injured when they contact the hot surfaces of overheated electric conductors, conduits, or other energized equipment. Another work practice that can result in electrical hazards is the improper use or repair of equipment, as well as the improper use of extension and flexible cords. Using electrical equipment in ways other than the manufacturer intends compromises the equipment's built-in safety features. Misuse of equipment may also damage equipment, which can lead to worker injuries. Electrical hazards are often a result of inadequate or faulty wiring. Poor wiring can increase the possibility of fires, power surges, and arc faults. Damaged, worn, cracked, or corroded electrical wires can also increase the possibility of electrical hazards. If a conductor is too small to safely carry the current flowing through it, a tool may draw more current than the cord can handle. Too many devices plugged into a circuit can overload it and heat the wires to high temperatures, melting the insulation and allowing the conductors to touch, which can result in a flash that ignites nearby flammable materials and starts a fire. Damaged insulation can also cause electrical conductors to make contact with each other, tools, or a worker's body. Loose outlets or outlet connections where the plug does not have a tight fit can also result in electrical injuries. Installations without proper grounding and defective equipment or tools can cause serious injuries to workers. There are occasions when the working environment contributes to or causes electrical hazards. Electricity and water are a dangerous combination. Dry skin has a fairly high resistance to electric current, but when skin is moist or wet, it acts as a conductor. This means that anyone working with electricity in a damp or wet environment needs to exercise extra caution to prevent electrical hazards. In atmospheres containing explosive gases, vapors, or combustible dust, even low-energy arcs can cause violent explosions. Air is a good insulator for low voltages. It cannot conduct electricity. However, if electrical insulating material is subjected to a high enough voltage, air can become an electrical conductor and electric current can flow through it. An electrical fault is any abnormal flow of electricity in a circuit. Select the objects to learn about situations in which electricity behaves abnormally. Circuits carry current through certain paths to perform certain functions. A short circuit occurs when current travels through an unintended path or takes a shortcut. The unintended path occurs due to an inadequate amount or lack of resistance, which results in too much current flowing through the circuit. This often occurs when bare wires touch one another, when wire connections become loose, or when another conductor is present. For example, if you put a knife in a toaster, the knife provides a shortcut for the current. The path created by the knife is easier for the current to move through than the toaster's highly resistant heating element. A ground fault occurs when an unintentional pathway becomes available, allowing the electrical current in the circuit to travel directly to the ground. The main danger of ground faults is the likelihood of a person becoming part of the unintended path through which the current flows to the ground. An overloaded circuit occurs when the circuit carries more electrical current than its design can safely handle, resulting in wires overheating, insulation melting, and the possibility of fire. Select each image to learn about the injuries that can result from electrical hazards. After reviewing the content, select the X to return to and learn about the remaining images. Shock occurs when your body, a conductor of electricity, unintentionally becomes part of an electric circuit. When you receive a shock, electricity flows between parts of your body or through your body to a ground or the earth. This occurs when your body completes the current path with both wires in a circuit, one wire in a circuit and the ground, or a metal part or other conductor that is carrying current. The occurrence and severity of the shock depends on the amount of current and the path it takes through your body. The longer the exposure, the greater the risk of serious injury. Long exposures at low voltages can be just as dangerous as short exposures at higher voltages. Current flowing through your body may cause your muscles to contract or freeze. When you freeze, you are unable to pull yourself free from the circuit. Freezing may result in injuries from collisions or falls. When working with very high voltages, an arc flash can occur when the bare energized conductors of different systems come together, causing a brilliant flash of light. An arc flash could occur from dropping a screwdriver into an electric panel, from compromised insulation, or from a loose connection on equipment. The length and duration of the arc flash is determined by the voltage, current level, and conductivity of the air that sustains the arc until a protective device stops the current flow. Arc flash temperatures can reach up to 24,000 degrees Fahrenheit, which is intense enough to vaporize metal. Once bare conductors touch and current flows, an electrical arc can form in the air gap between the conductors. An arc flash at higher current flow can stretch between the conductors, from inches at voltages below 600 volts to several feet at voltages over 4 kilovolts. Exposures to arcs and arc flash can result in severe burns due to the intense heat and eye injuries caused by high-frequency ultraviolet light emitted by the arc flash. When an arc flash reaches or exceeds 20,000 degrees Fahrenheit, an arc blast explosion can result due to the rapid vaporization and expansion of the moisture in the air. Arc blast pressures can exceed 2,000 pounds per square foot, which is strong enough to knock workers down or throw them across the room. Arc blast explosions can result in hearing damage due to sound pressure from rapid air expansion and wounds from flying shrapnel and molten metal. Two types of burns can potentially occur when you work with electricity: electrical burns and thermal burns. Electrical burns occur when electric current flows through tissues or bone, generating heat that can cause damage to your body. Electrical burns are among the most painful and hardest to heal. They are very serious and require immediate medical attention. Thermal burns occur when your skin touches the hot surface of overheated electric conductors, conduits, or other energized equipment. They frequently occur from just being close to an electric arc. Fire may also occur from an electric arc. These types of fires may result in your clothing catching on fire, leaving thermal burns on your body. Given the serious hazards of working with electricity, workers must have sufficient skills and training to do so safely. Select each object to learn about electrical worker roles, responsibilities, and qualifications. As part of their electrical safety program, your employer must have training and retraining requirements and qualifications. These requirements and qualifications are part of your employer's qualified worker program and are customized specifically to your organization. A qualified worker's knowledge allows them to perform one or more specific tasks, and they must have sufficient safety training to recognize and address the specific electrical hazards associated with those tasks. These workers must also demonstrate proficiency in safely working on energized equipment and using test instruments and meters. Your employer must document each worker's training and proficiency tests. A qualified worker must ensure the safety of unqualified workers by using safe work practices. An example of this would be shielding unqualified workers from exposed electrical systems and installations. A qualified electrician is a tradesperson specializing in the electrical wiring of buildings, stationary machines, and related equipment. This type of electrician has more extensive safety training and more experience performing a variety of electrical tasks. A company does not have to turn to a qualified electrician for every electrical task, as long as the worker assigned to perform the task receives adequate training and meets the criteria of a qualified electrical worker for that specific task. An unqualified worker does not know the electrical equipment or has not received safety training on the potential hazards involved. Unqualified workers are generally non-electricians, such as general maintenance workers or painters, who are not expected to work on live electrical equipment. Here is a practice exercise to test your knowledge. Select each term or unsafe condition and drag it to its corresponding description. When you're finished, select Check My Answer to see how you did.
What's that?
Well, it used to be the electrical panel, but this isn't where we left it. Originally, we had it in the center of the room, away from any clutter and well ventilated. I'm guessing the tile setters moved it so that they could lay their tile and then didn't put it back when they were done.
And that was enough to cause a fire?
Well, not necessarily. Without proper ventilation, the panel may have overheated, but that would have caused the breaker to trip before anything got hot enough to catch fire.
Then why did we have a fire?
Electric protection devices are safety controls that can limit injuries to workers and damage to equipment when circuit problems, faults, occur. Protection devices detect abnormal electrical conditions and will initiate appropriate corrective actions. For example, power outages may result from an overloaded circuit, a short circuit, or a ground fault creating unsafe conditions. Protection devices limit the loss of power to the rest of the system while protecting equipment and people. Select the objects to learn more about electric protection devices. A ground fault circuit interrupter, or GFCI, protects people from severe or fatal electric shocks resulting from ground faults, which occur when current leaks from a circuit. This circuit protection device shuts off an electric power circuit when it detects that current is flowing along an unintended path, such as through water or a person. GFCIs are the only type of circuit breaker that operates before stray current reaches a level hazardous to workers. GFCIs are available for electrical panels or in individual electrical outlets. They may attach or be built in to cords. Fuses and circuit breakers protect wiring and equipment by limiting the amount of current a circuit will carry. They trip or break the circuit when the current flow becomes excessive and unsafe. This prevents the overheating of wires that can melt electrical components or cause fires. An arc fault circuit interrupter, or AFCI, sometimes also referred to as an arc fault detection device, or AFDD, protects against fires resulting from arcing faults. This device shuts off an electric power circuit when it detects an electric arc, preventing potential electrical fires. Some devices may have both a GFCI and an AFCI. Using insulators to wrap electrical wires, cables, or equipment can protect workers and equipment. Insulated tools are regular tools like screwdrivers, pliers, or wire strippers, for example, that are covered with an insulating coating. They are dielectric, which means no part of the tool's insulation will conduct electricity if it comes into contact with voltage less than 1,000 volts. Manufacturers may design cord-connected electric tools, like drill motors, with double insulation. These types of tools have 2 layers of non-conductive material on the part of the tool you would typically touch or grasp, like the handle. Double insulated tools are easily identifiable by a square icon with the capital letter D inscribed inside it. Grounding systems are a safety control that connects specific parts of the electrical system to the ground. Grounding does not guarantee that you won't get shocked or be injured, but it will reduce the risks. Select the objects to learn more about grounding. A circuit is made of 2 wires, a hot wire and a neutral wire. Normally, current will return to the ground through the neutral wire. A grounding wire is a safety wire that intentionally connects from the case or outer part of electrical equipment down to the earth. It does not carry electricity under normal circuit operations, but carries electrical current only when conditions could be potentially dangerous. Grounding prevents surges of electricity, protecting your equipment and the people in contact with it from accidents or injuries. Grounding electrical equipment ensures that any current resulting from a malfunction of the circuit will be diverted to the earth, protecting both you and your equipment from shock or damage. You can find an equipment ground on a 3-pronged plug. The 3rd prong indicates that the tool or device has a grounding safety feature. Many plug-in hand tools and devices have a grounding system for safety. The 3rd prong on the cord plug fits into the round grounding slot on an outlet. Tools marked with a double insulation icon do not have a 3-pronged plug, but are safe to use because they are double insulated, minimizing the risk of short circuits. An Assured Equipment Grounding Conductor, or AEGC, safety program is a written program your employer implements that documents the condition of power tools and extension cords. The program requires strict inspection and administrative processes and covers all equipment connected by cords and plugs available for your use. Your employer must designate 1 or more competent persons to implement the program. The AEGC program's goal is to prevent electrocution by ensuring the grounding wire is electrically continuous from the power tool to the power source. This program is typically in place when GFCIs are not available. Your employer must keep a written description of the AEGC program and their specific procedures for equipment inspections and tests, as well as their testing schedules, at the job site. The AEGC program requires a qualified worker to complete 2 tests on all electrical equipment. The first test, a continuity test, ensures that the equipment's grounding conductor is electrically continuous. Qualified workers perform this test on all cord sets, outlets, and cord and plug connected equipment which require grounding. They will also perform a terminal connect test on all receptacles and plugs to ensure a connection between the equipment grounding conductor and its proper terminal. Your employer must record and maintain a record of current tests and ensure that the equipment that has failed a test is not available for use. The written program description and the recorded tests must be maintained at the job site and made available to any affected employee upon request. A qualified worker must test electrical equipment before the first use and then again after any incident in which you suspect that the cord was damaged, such as the cord getting run over by equipment or a vehicle. They must also test again before the equipment returns to service following repairs. Testing must occur in intervals not to exceed 3 months. If you can ensure the cord sets or receptacles are in good repair and are free from exposure to damage, a 6-month interval is acceptable. Your employer is responsible for providing you with a workplace free from recognized hazards. An electrical safety program is a safety control that helps them do this. An electrical safety program describes safety principles, policies, procedures, training requirements, and processes that will minimize harm and injuries at the workplace. This program should define roles and responsibilities, identify workplace hazards, and analyze risks. It allows for regular assessments of the program's effectiveness and documents plans to implement needed improvements. Your employer will assign the responsibility of an electrical safety program to an employee with a complete knowledge of electricity, electrical work practices, and the appropriate standards. Everyone must follow the program to make it effective. Select each object to learn more about an electrical safety program. Your company's electrical safety program identifies the process a qualified employee uses before work starts to identify hazards, assess risks, and implement risk controls according to a hierarchy of risk control methods. In order of priority, from most to least effective, the control methods are elimination, substitution, engineering controls, administrative controls, and personal protective equipment, PPE. One component of an electrical safety program is job briefings. Before starting each job, a competent person conducts a job briefing with everyone involved with the work. Each job briefing covers associated hazards, work procedures, special precautions, energy source controls, PPE requirements, and information on the energized electrical work permit, if required. As part of their electrical safety program, employers must have training and retraining requirements and qualifications. If your work exposes you to an electrical hazard, your employer must provide training on the specific hazards associated with electrical energy, safety-related work practices, procedural requirements, and the relationship between electrical hazards and possible injury. The type and extent of training depends on the amount of risk your work involves. Employers must verify employee training annually and document it with the content, the employee's name, and the dates of training and when the worker demonstrates proficiency. An electrical safety program calls for a system of detailed audits. Your employer's supervisory representatives will conduct and document an administrative audit. This audit verifies that the electrical safety program's written principles and procedures are in compliance with the standards. Fieldwork audits, or inspections, verify that workers follow the procedures of the electrical safety program. If the audit determines workers are not in compliance with the program procedures, an employer's representative determines the cause and takes corrective action, which could be discipline, retraining, or process improvement. Field audits occur yearly at a minimum, but as a best practice, audits are ongoing and happen weekly. Electrical accidents are largely preventable through safe work practices. An electrical safety program should include practices and policies that protect workers from electrical hazards. These practices and policies include following lockout, tagout procedures, de-energizing electrical equipment before inspection or repair, and using appropriate personal protective equipment, PPE. The program should also include energized work permit procedures, as well as other safety precautions, such as using and maintaining electric tools properly, exercising caution when working near energized lines, and avoiding wearing jewelry and smoking. Guarding is a safety control that will protect you from electrical injuries by locating or enclosing electrical equipment in a way that ensures people do not come into contact with its live parts. Any electrical equipment that is 50 volts or more must be guarded to prevent access by unqualified persons. Select the images to learn how proper guarding can protect you from the risks of electrical injuries. You can protect workers by elevating electrical equipment on a suitable balcony, gallery, or platform at least 8 feet above the floor or other working surface. You can guard and protect electrical equipment in a cabinet, room, vault, or other similar enclosure. Employers should ensure that installations that are over 600 volts and open to unqualified persons are made with metal enclosed equipment, enclosed in a vault, or in an area controlled by a lock. These secured areas must have appropriate caution signs posted to warn unqualified persons of the hazards. Separate electrical equipment using permanent, substantial partitions or screens. A wall, screen, or fence at least 8 feet in height is considered adequate to prevent unauthorized access to an electrical installation. Guard equipment containing exposed live parts with warning signs at entrances that forbid unqualified persons from entering. Lockout, tag-out procedures are a safety control that can prevent workers from accidentally starting up energized equipment that is being maintained or repaired. Select each image to learn about lockout, tag-out practices and procedures. After reviewing the content, select the X to return to and learn about the remaining images. The first step before beginning the inspection, repair, or maintenance of any equipment is to follow the written procedure to isolate all energy sources to prevent accidental startup of the equipment. This is done by using a device that locks the energy source and a tag that indicates that the energy on that piece of equipment is out of service and isolated. It is critical that you never attempt to remove a lock or tag unless you are the person who placed them onto the system. Only authorized employees should apply and remove their own devices. There are 7 steps in the lockout-tagout procedure. Step 1 is to communicate. Notify all affected employees that the machine or equipment must be shut down and locked out. Step 2 is preparation. In this step, the authorized individual prepares for lockout-tagout by identifying the specific equipment hazards and developing a plan for controlling the equipment's energy. Step 3 is to shut down the machine or equipment and notify any employee affected by the shutdown. Step 4 is to isolate the equipment from all sources of energy. This may include turning off the power at a breaker or shutting a valve. Step 5 is to lock and tag out the equipment. The authorized employee does this by applying a lock and a tag to the energy isolating device in a way that prevents anyone from inadvertently altering the energy source to an unsafe position. In Step 6, the authorized individual looks for any hazardous energy that has been stored or that remains within the machine and ensures that the residual energy is made non-hazardous and inaccessible to others. Lastly, in Step 7, the authorized individual verifies that the equipment has been properly isolated and de-energized. Authorized individuals will use locks for lockout-tagout that require excessive force, bolt cutters, to be removed. Each lock must have a unique key and be dedicated for lockout-tagout purposes. Authorized workers generally use locks for lockout-tagout that have colored plastic coatings to distinguish them from utility or general service locks. Your company should use locks that look identical to each other so that they are easily identifiable. Authorized individuals will place tags with locks to indicate that a piece of equipment will not operate due to repairs or maintenance. The authorized individual will place tags at each point where equipment or circuits may become energized. Tags communicate danger and warn workers not to start, energize, operate, or do anything with that equipment. Tags may display red text to emphasize the warning and may include identifying information, name, department, and possibly a photograph for the authorized individual who placed them. Never attempt to remove a tag unless you are the person who placed it. Workers may require additional equipment to isolate an energy source. For example, if you have machinery that uses a unique valve to turn on and off its energy source, a conventional valve cover may not work. In this case, an authorized individual might wrap a chain around the valve handle and lock the chain in a way that prevents anyone from turning it. Other examples of additional equipment include fasteners, hasps, and gang lockboxes. When multiple workers must maintain control over an energy source, they may use a group or gang lockbox. This is usually a metal box that has a key to the locked-out equipment inside. The box has holes through its lid and side for multiple locks, so all workers involved in the maintenance or repair can apply their lock. This prevents a single worker from retrieving the key and energizing the system while others are still working on it. Personal protective equipment, PPE, is employer-provided clothing and equipment that may be the only thing standing between you and serious injury. In order for this safety control to be effective, you must wear PPE that is appropriate for the specific parts of your body that require protection and for the work you'll be performing. PPE for electrical work falls into hazard risk categories based on the type and degree of hazard ranging from 1 to 4, with 4 being the most protective. Select each object to learn the PPE requirements for those working with electricity. Wear non-conductive safety glasses or goggles for all levels of electrical work. Glasses with side protection provide the best protection from flying objects. If your eyeglasses have metal parts, prevent electrical contact hazards by wearing safety glasses or goggles over your metal frames, and also wear a protective face shield over your safety glasses or goggles. Use hearing protection when working within an arc flash boundary to protect your hearing in the event of an arc blast. Use non-conductive head protection whenever there is a danger of head injury due to electrical shock, burns, or from flying objects resulting from an electrical explosion. Hard hats rated as Class E are insulating safety hats, usually made of plastic or fiberglass. Manufacturers make and test Class E hard hats to successfully withstand 20,000 volts. Do not use hard hats that have any type of ventilation, since they are typically not voltage rated. An arc-rated wraparound face shield protects your forehead, chin, ears, and neck from heat and arc flash blast hazards. Balaclavas, or an AR flash suit hood, provide greater protection against thermal energy. You must also wear safety glasses or goggles under hoods or shields. You may wear plain leather work gloves for electrical work that falls into arc rating categories 1 and 2. If you are performing electrical work that falls into arc rating categories 3 and 4, you'll need to wear arc-rated gloves. Wear heavy-duty leather footwear or dielectric footwear, or both, to protect from electrical hazards such as static discharge or electric shock. When working with electricity, wear non-conductive protective clothing. Next to your skin, wear only natural fabrics such as cotton or wool that will not melt. Wear arc-rated long-sleeve shirts, long pants, jackets, coats, bib overalls, or coveralls. Never wear clothing made from highly flammable materials such as untreated polyester, nylon, acetate, or rayon. You must wear arc-rated flash-resistant clothing that is arc-rated at or above the hazard category to which you are exposed. At high heat exposure levels, even unrated natural fabrics could ignite. Lockout, tag-out procedures often involve uninsulated connections within cabinets or enclosures. You could encounter circumstances in which you might need hardcover plastic shielding and guards to protect you from uninsulated wire. Most electrical tasks will require you to use insulated tools and a voltmeter to measure the voltage in an electrical circuit. Depending on the work you are performing, you may need personal fall arrest equipment or other PPE. Select and drag each safety control to the appropriate category. If the item is placed in the correct category, it will remain in place. If it is placed in an incorrect category, it will return to the list where you can try again.
The carpenters did complain that the breaker was tripping when they tried to use more than one tool at a time. If they'd given me a minute to come check it out, I could have... Hold up.
What's that?
Looks like they tried bypassing the breaker. That, combined with running multiple tools at a time, would explain how quickly the panel overheated and ignited. The adhesive used by the tile crew is flammable, and the clutter didn't help either. I'm glad they made it out safely, but they're not coming back to work here.
No one is. We've been shut down, but we're going to use the downtime to do some serious training and add precautions wherever we can. I'm not taking any more chances.
Select each image to learn about important preparation and installation practices that will protect you from electrical hazards and injuries. After reviewing the content, select the X to return to and learn about the remaining images. To ensure electrically safe work conditions and reduce the risk of electrical injuries, you must faithfully follow the process of turning off the power, verifying the power is off, and then ensuring the power stays off while you perform work. The steps to follow anytime you are working with electrically energized equipment are: identify the power sources, disconnect the power sources, verify that the power is off, log out, tag out, and then verify again that the power is off. Prior to beginning electrical work, you will need to do a thorough inspection and evaluation of the equipment you'll be using to look for any defects or damages. Inspect for contamination from paint, plaster, cleaners, abrasives, and corrosives. Look for equipment parts that may be broken, bent, cut, or deteriorated by corrosion, chemical action, or overheating. Evaluate cord sets, plugs, receptacles of cord sets, and attachment caps, looking for defects or damages such as missing or deformed pins, damaged insulation, and internal damage. Never use damaged or defective equipment. Proper use of electrical equipment requires that you follow the manufacturer's instructions located on the equipment label. Do not use electrical equipment unless there are descriptive markings that identify the organization responsible for the product and provide voltage, current, wattage, or other necessary ratings. Equipment should have clear markings on each motor, appliance, service, feeder, and branch circuit at its disconnecting means or overcurrent device to indicate its purpose. Equipment markings and labels must be durable enough to withstand environmental conditions. Safe operation of electrical equipment requires that there is sufficient access and working space around it. Storage areas are not appropriate places for electrical equipment due to flammables and inadequate working space. Do not place equipment in damp or wet locations or in areas exposed to excessive temperatures. Do not place equipment in areas exposed to gases, fumes, vapors, liquids, or other agents that may have deteriorating effects. When mounting equipment, firmly secure it to the mounting surface. Ensure there is adequate clearance between the top of the surfaces and adjacent surfaces to allow rising warm air to easily dissipate. If equipment has ventilated openings, ensure the installation avoids obstructions by walls or other equipment that might reduce or cut off free-flowing air. Ensure you are mounting the equipment in a location that will keep it cool, prevent overheating, and provide adequate airflow. Select each image to learn about hazardous zones and approach boundaries. After reviewing the content, select the X to return to and learn about the remaining images. A best practice when working with electrical hazards is to be aware of hazardous locations and approach boundaries. Hazardous locations are areas or zones where fire or explosion hazards may exist due to the presence of flammable liquids, gases or vapors, or combustible dust or ignitable fibers. In these hazardous zones, electrical equipment can become a source of ignition. Common sources of ignition include arcs and sparks resulting from the normal operation of the equipment, The high temperatures of some heat-producing equipment and electrical equipment failures, such as short circuits, can also be sources of ignition. To protect workers, arc flash approach boundaries establish lines that only qualified workers can cross. Working in a hazardous zone requires approval of the equipment, wiring, and installation methods based on the ignitable or combustible properties of the specific substance present in that zone. It's critical that you only use equipment with markings showing the zone and operating temperature or temperature range for which it is approved. IEC classification uses zones to classify hazardous locations. The classification system starts with identifying the type of substance present in the location. Hazardous location zones are divided into two categories based on the type of substance present. One category is for locations where gases, vapors, and mists are present in sufficient hazardous, ignitable, or explosive concentrations. These locations are classified as hazardous zones 0, 1, and 2, depending on how often that hazard is present in that location. The other category is for locations where combustible dust and ignitable fibers are present in sufficient hazardous, ignitable, or explosive concentrations. These locations are classified as hazardous zones 20, 21, and 22, depending on how often that hazard is present in that location. After classifying the type of substance present in the hazardous location, the zone classification system identifies how often that substance is present and divides the frequency of occurrence into three categories. These categories are Zone 0, gases and vapors, and Zone 20, dust and fibers, in which substances are continuously present and the hazards are present during normal conditions or for long periods of time. Zone 1, gases and vapors, and Zone 21, dust and fibers, in which substances are present intermittently and are likely to occur under normal operating circumstances. And Zone 2, gases and vapors, and Zone 22, dust and fibers, in which substances are abnormal, are not likely to occur under normal operating conditions, and are present only for a short period of time. Class and division refer specifically to the categorization of hazardous locations. These locations pose a higher risk of fire or explosion due to the presence of flammable liquids, vapors, gases, or combustible dusts. Class identifies the general nature of the flammable material present, for example, vapors, liquids, or dusts. There are different class designations depending on the specific material. Division specifies the specific hazardous conditions within the location based on the ignitability of the material and the frequency of flammable concentrations in the air. This classification system helps determine the appropriate electrical equipment selection and installation methods for hazardous locations. For example, a Class 1 Division 1 location would require explosion-proof electrical equipment to minimize the risk of ignition. In preparation for a job briefing for work on or near energized equipment, qualified workers will identify approach boundaries using the National Fire Protection Association or your employer's Safe Work Practice tables. These boundaries are 1. Arc flash, 2. Limited approach, and 3. Restricted approach. They establish lines that only qualified workers can cross. Unqualified workers can cross the limited approach boundary if they are accompanied and directly supervised by a qualified person and are fully aware of the possible hazards. Under no circumstances can an unqualified person cross the restricted approach boundary. Work in all boundaries requires an approved permit, a job briefing by a qualified person, and appropriate PPE. Using equipment in ways for which it is not designed may result in damage to the equipment and injuries to you and your coworkers. Select the objects to learn about some common misuses of cords, cables, and electrical equipment. Improper use of cords and cables can cause them to overheat and cause fires. Cords and cables are more vulnerable than fixed wiring, since they are exposed, flexible, and unsecured. Cords and cables can damage easily due to aging, contact with doors and window edges, punctures from staples or fastenings, and abrasions from adjacent materials or activities in the area. Before using cords and cables, ensure they are properly rated for their intended use, indoor or outdoor, and that they meet or exceed the power needs of the device you are going to be using. Using equipment outdoors that is labeled for use in dry indoor locations can be dangerous. Do not use circuit breakers or fuses with the wrong rating for overcurrent protection. A heavy reliance on extension cords is an indication that you have too few outlets to address your electrical needs. Never overload extension cords or attempt to plug them into one another. The best solution to this problem is to install additional outlets. Inspect extension cords for damage before use, checking for cracked or frayed sockets, loose or bare wires, and loose connections. Keep outdoor extension cords clear of snow and standing water. Do not nail or staple extension cords to walls or baseboards, or run them through walls, doorways, ceilings, or floors. Covering a cord prevents heat from escaping, resulting in a fire hazard. Do not strain cords, since doing so can cause the strands of one conductor to loosen from under the terminal screws and touch another conductor. Do not use shop-fabricated equipment or tools that are not in compliance with federal regulations. Do not use outlet boxes designed to be mounted by fitting them with a power cord and placing them on the floor. Do not substitute an extension cord for permanent wiring, or use spliced, taped, or modified cords that are not continuous or are not the correct type. Do not use an extension cord or power strip with heaters or fans, since doing so could cause the cord to overheat, resulting in a fire. Use only 3-wire type, extra hard usage extension cord sets with portable electric tools or appliances. Only use 3-prong plugs and 3-slot outlets so that the grounding is functional. Removing a grounding prong from a plug in order to make it fit in an outlet or extension cord is dangerous and could lead to shock if the device short circuits. Do not attach ungrounded 2-prong adapter plugs to 3-prong cords and tools. Here is a practice exercise to test your knowledge. Read each statement at the left. Select the column at the right that would identify the statement as either true or false. When you're finished, select Check My Answer to see how you did.